All right. So thank you all for being here. I mean, I prepared a talk that is mostly a review of different things that have happened in the last, I would say, 10 years in the area of deep learning, and especially in the area of the foundations of deep learning. And the reason I put this together is actually several reasons. One is that quite often when I talk with people here, students, researchers, people that we work with, I mean, some of these questions come up, right? Questions about how big should my network be? How big should my data set be? Right? So these are important questions that are coming up in practice all the time. And the second thing is there is this conventional wisdom in the community that somehow deep learning neural networks are not very, they don't have mathematical foundations. It's more like an engineering, trick or something. And again, that's not really true. I mean, maybe it was true some years ago, but there has been a lot of work, actually, theoretical work, great mathematical work, excellent work in the last few years. And I don't know if people are still aware of it because it's not in the textbooks, right? So if you open the textbooks on machine learning, on AI, they don't talk about this stuff. It's too recent. All right, so a little bit of the outline of the talk. So I will start with a very, very brief overview of very fundamental concepts, in case somebody is not super familiar with these things. And then I will mostly talk about four subsets, right? The first question is, do deep neural networks overfit, right? The conventional wisdom is that if you have a model that has too many parameters, it will start overfitting. Well, that's not true, actually, for deep neural networks. And it's called the double descent phenomenon, and it's very interesting. The second thing that we will discuss is, all of these networks are trained with stochastic gradient descent or some variations of that learning algorithm. It's a very basic learning algorithm. You learn about it in high school, most likely. But it actually works surprisingly well, even in problems that are non-convex optimization problems. So how is this even possible, right? So that's another fundamental question. We will discuss the role of the depth and the width, right? So if you're working with neural networks, a very common question is, how wide should they be? How deep should they be, right? So what does the width and the depth, how do you choose them, right? I mean, what is the theory behind the choice of the width and the depth? The last part is something actually that we have been working on. So I admit that part maybe it's not so foundational as the other things. I wanted to include a little bit of our work just to promote it a bit and let you know what we like doing with my students. Okay, so let's start with the background. Basically, for any machine learning model, right, you have the following things, right? This is the anatomy of a machine learning model. Of course, there is the underlying distribution given x, what is y, right? This is the target function that you are trying to learn. So think of it as x being images and y being the labels of those images, whether they're cats, dogs, or something else, right? So ideally, you would like to learn this function from data. Now, in every machine learning model, you have a loss function, which is the thing that you try to minimize, right? That's essentially presenting what is your task, what you try to accomplish in that task. You have the hypothesis set. So this is basically the set of different functions, right, that you consider when you try to find the function f, right? So if your hypothesis set is very rich, you have many different functions to choose from. If it is a very small hypothesis set, that limits your model. And of course, there is the learning algorithm, which is it's taking the training data, it's taking the loss function, which you try to minimize. It's taking this set of possible hypotheses or functions, and it's giving you one final answer. Let's call it G, right? And this function G, again from X to Y, is trying to be as close as possible to the underlying target function F that we don't know, right? And of course, there is the unknown input distribution here, the different values of X that we can get. That is used twice in the model. One is to give you the training data, right? So x1 through xn, these are the training examples. And it also gives you the data that you will need for your testing, for your evaluation of the model, right? Any questions so far about, actually, let me show you one more slide and then I'll ask you a question. So an example is the simplest example, right, of a machine learning model is if you do linear regression. In that case, this hypothesis set here, right, can be described basically by this linear equation, right? It only has a couple of parameters. If you're doing regression, right, you're trying basically to minimize this absolute distance between the actual values y and the estimated values y, right? So you're trying to minimize this there. And so that's your cost function or loss function. And of course, you have to have an algorithm, right, for minimizing that function. Now, of course, for linear regression, it's so simple that you can actually derive what is the optimal choice of the parameters theta 0 and theta 1. If you have a more complicated model that is non-linear and so on, you will need to rely on approximations, algorithms like gradient descent. So far, so good? All right, so let's talk a little bit about a specific class of machine learning models that are called neural networks. As you know, they are very powerful in the sense that that space of possible hypotheses is very big, it's very broad compared to simpler models like regression. So in a neural network, you have always individual neurons, or we call them hidden units sometimes, and each of them can be represented by a mathematical function, which is the following. Basically, you have a number of inputs, right, x1 through xn. Each of them is weighted by some weight w. So you take the summation of those weighted inputs, and there is also a bias there, which is this constant v. It's nothing super tricky. You can actually incorporate it into the sum. And then the important thing is that we have a nonlinear function f, which we refer to as the activation function. And that function is giving it the model the nonlinearity. If you don't have the nonlinearity, the model is really a trivial model. It cannot do anything useful. So it all starts from that nonlinearity. These nonlinearities can be of many different types, sigmoid and so on. The one that has been quite popular in the last, I would say, 10 years is the ReLU function, which is actually, it's continuous, but it's not smooth, right? At this point here, there's a discontinuity in the derivative. The reason people like this function is mostly because it can be implemented in hardware, so in comfortable ways, convenient ways. Yeah, I mean, it's basically not like as smooth, right? That's the sigmoid function. Now, of course, a single neuron cannot do much. So we have typically networks of neurons that are basically in different layers, right? And that determines the depth of the network, how many layers you have, and also the width, right? The width doesn't have to be the same in all layers. In this case, it is every hidden layer has 5 units. And you can represent this mathematically again essentially the way to read this is that X is the vector of inputs. It is multiplied by the initial weights here that are given by this matrix W0. The dimensionality of the matrix is the number of inputs times the number of hidden units in the first layer. Then you have this, the nonlinear function, the activation function. It applies basically to each of these, to the output of each of these weighted products. And then, you keep doing that, right, layer after layer. So you can represent basically the whole network as a sequence of matrices, one for each of these layers, right? Now, the loss functions that people use are, there are thousands of loss functions out there. If you look at the literature, depending on the task, actually, sometimes this is an interesting research question. What is the best loss function for a given task? But the ones that people use more are, you have here the cross entropy function, which is used for classification problems typically, right? Basically for every possible, let's say, class, right? Typically only one class is correct. So only one of these Y terms will be one, the rest of them are zero. And then you also consider what is the logarithm of essentially the likelihood that the network gives for that class, right? The correct class. So you would like the model to give a high likelihood only for the correct class and a very low likelihood for all the other classes. But there are many other loss functions. What I want you to see here is that the loss function can also be nonlinear, right? So it's not only the nonlinearities that you get from the activation functions. You also have to solve an optimization problem which is nonlinear because you have to minimize these functions. One of them. Now, what makes things really tricky is that if you look at essentially the loss landscape, right? So you're trying basically to find the optimal parameters of the model, the parameters that will minimize the loss. Okay, if you are dealing with something like this, well, maybe that is actually a relatively easy problem to minimize, an easy function to minimize, almost convex. But in reality, the loss landscapes for neural networks look like this, right? And it's very easy to get trapped on local minima, they have saddle points, all kinds of difficulties from the optimization perspective. So for a long time, people knew this, right? And for a long time, I remember, like when I was in graduate school, that was in the 90s, late 90s, people would say, don't work on neural networks. It's hopeless. I mean, first of all, you will never be able to find the optimal parameters. You will never be able to solve such an optimization problem. Do something else with your life, right? And I believe in that. Anyway, so of course, we talk a lot about gradients when you are trying to minimize any function. In this case, it's a function, of course, of many variables, right? And just to remind you what the gradient of a multivariate function is. And the famous algorithm that people use for learning, essentially, in deep neural networks and in many other models is stochastic gradient descent. The basic idea is that you basically have, it's an iterative algorithm, right? You have some weights for your network right now, and then you compute the weights for the next, let's say, time instant by basically looking at the direction, right, of the gradient of this function. So there is a learning rate, which determines, of course, how fast you are doing these updates. And in principle, this is like the algorithm that people use. Of course, there are many engineering hacks on exactly how you can do this, but this is the very basic idea. So in optimization terms, this is called the first order method, right? Because you only rely on the first order derivatives. You don't look at second order derivatives. And Of course, you have to be very careful not to get trapped in any kind of local minima. You're looking for the global minimum of the function, of the loss function. So there are many different variations of the stochastic gradient algorithm, whether you are doing it in small batches or whether it is actually stochastic or not stochastic, and so on. Now, again, all of this is overview. All of this is essentially what you learn when you take an introductory class in machine learning. So I'm sure you have seen this kind of curves. They basically tell you that if you have a model and on the x-axis you have the parameters of the model, the complexity of the model, right? Here on the y-axis, let's say you plot something like the loss or the error that your model makes. Basically, the typical trend is that as you increase the number of parameters, your training error, right, can get smaller and smaller. You can basically fit with your data, the training data, more and more. But I'm sure I'm sure you know that the conventional wisdom, at least, is that after a certain point, your test error will start going higher, right? So this is called the overfitting effect. Visually speaking, let's contrast these three pictures here: underfitting, overfitting, and the middle one is a good fit. If you have a model with very few parameters, let's say only 2 parameters, it's just a straight line, linear regression, then of course you will have significant bias, right? Your estimates will be very far from the actual values, even for the training data. If you have a very, here, right, and you have a very large number of parameters, the problem is that you may fit the training data extremely well, and get a 0 training error, but you may have this kind of spurious ups and downs, think of it this way, right? That do not really capture what happens with the data, and then you may have a large test error when you apply your model in some different data that is not in your training data set, right? And the conventional wisdom, at least, was that you want to be somewhere here in the middle where the training error is not actually 0, and you hope for the test error to be somewhere in the minimum. And people were trying to find this sweet spot by also having a separate data set, the validation data set that they would use as they train the model. Right, and this was kind of referred to in statistics, very fundamental stuff like the bias variance trait, right? That your model, you can basically, if you are at one extreme, you can, minimize the variance of your estimator, but have actually large bias. If you move to the other extreme, you will have large bias but low variance, and you want to be somewhere in the middle. All right, so yeah, this is exactly what I said before. This is just showing things in a little bit more detail. The error rate, the model complexity or number of parameters. The green curve is the training error, which drops as you have a model with more and more parameters. And the red line here refers to basically your test error. Ideally, you would like it to be somewhere right in the middle, so to speak, that sweet spot. That was this is what you learn when you open a text, okay? And all of this has been challenged in the last few years for reasons that I will tell you. Yes.
You're in the testing phase, lower than the training phase. Examples from
the error in the so this is typically, it's not this way, right? I don't know. This is a cartoon. It's not like a real, but typically, your error rate will be lower for the training data set. Right. Good point. Okay. So all of this was overview. Now let's start looking at these different interesting things that happened in the last few years. So it all started, let's talk about double descent first. It all started with some empirical observations, from people that were actually training big models, like the ResNet 18 network. You may know about it. It's a convolutional network. Actually, it uses a trick called residual network, residual connections. It's a very big network, right? Basically, they had here the test and train error. Here they have something that represents the parameters, the number of parameters. It's not, don't take this like literally. It doesn't mean that it has 60 parameters, right? It's a parameter that represents the width of the network. So the actual number of parameters is in the thousands or millions, right? And what they observed was that the training error, you can have a network that is bigger and bigger and bigger, and you can make it actually to go to zero. And the test error, it had this initial, descent and then increase, which is what the textbooks are talking about, right? But then, if you keep trying for larger and larger models, it starts having a second descent, a second decrease, right? That's why they call it the double descent phenomenon. And the test error that you will get in that regime sometimes is actually lower than this sweet spot. You can get an even lower test rate, error rate than this sweet spot. So of course, when people look at that, it was very strange, right? Because it goes against everything that we know about machine learning, and all the fundamentals are being questioned right now. So there were a sequence of papers published around 2020. One of them, the one that I want to talk a little bit more about, is this PNAS paper by these people that you see here. And I want to focus on the central theorem of this paper. Just tell you basically what these people actually did and give you the intuition. Now, if you want to see the proof, I mean, it's 10 pages proof, so it's probably not the right place to see it here. But it is very interesting, and if you want, it relies a lot on something called learning theory, which is a part of computer science that focuses on the mathematical foundations of machine learning. So let's look at their theorem and the setup. So we start with a training data set that includes n training examples, right? And think of them as the image and the label of the image, x, y. And so we got this training data set by sampling independently, right? From some, this has to be a compact domain. So we're not talking about some very pathological data sets here. I mean, it has to, topologically speaking, it has to come from this compact domain. D, by the way, is the dimensionality of the x's, right? So if you have images, the number of pixels times the number of pixels, right? The number of pixels in the image. And there is some unknown target function, x star. This is the function that we try to find, right? This function, if you knew it, it will tell you for each image what is the right label for it. Okay. All right. So this is one. The second thing. Oh, by the way, here H infinite is this space, right, of all the possible hypotheses, all the possible functions we're considering. Okay. Now let's start with another function H, which represents basically what your model, say your neural network, produces, right, as the approximation of this function H star. So this is another hypothesis, and the requirement is that this interpolates perfectly well the training data, right? So in order to satisfy this requirement, we have to have a model that is sufficiently large, right, to perfectly fit the training data. We're talking about a training error of 0. Okay, then if this is true, the theorem says that for any target function, right? Again, this is my training data set, independent, identically distributed in this compact space. And if I have basically, that, the y's have the correct labels, the correct values, then I can find basically some constants, A and B, okay, no worries, such that for any function h that strictly interpolates the training data, I can bound with high probability the maximum error between the target function and the function, this interpolating function that my model produces, right? So let's try to understand what this bound is, right? This is basically two different terms, right? Think of this term here that shows how this bound depends on how many training examples I have. Of course, n over log n, right? So this increases with n. But considering here also that, so if the dimensionality is constant, right? If I don't play with the dimensionality, obviously the more data I have, the tighter will be the bound between the target function and what my model predicts. The dimensionality here is important because it basically means the higher the dimensionality of the data, the slower this decrease, the larger essentially the error bound will be. But we really care about these norms here. So what are these norms? This is essentially a norm in the function space X infinity where think about it as it's a norm that quantifies how smooth the function is, right? The higher the norm, the less smooth the function is. The lower the norm, the smoother the function. Did I say this correctly? The lower the norm, the higher the smooth. Sorry. This function is the target function. It's fixed. You cannot change that, right? That's a constant something. Because this is the target function you're trying to find. So if you want to basically minimize this bound, you will have to search, your model will have to produce a function h that gives you the smallest possible norm. Right? Then this term here will be minimal, and the error between these two functions will be as small as possible. So this is essentially the essence here of this theorem. It says that you need, in order to minimize that error between the correct function and the function that your model predicts, you need to come up with function h that is as smooth as possible, right?
So,
yes.
With respect to the parameters, or
smooth with respect to essentially the function itself, right? So the function, think of it as that function space, has to be as smooth as possible, but still interpolate the data, right? So let me give you an example that may help with this. This is an example where we have, maybe 8 training examples, which are these red dots. And you can interpolate these points either with the blue function, which relies on just 40 features, think of them as 40 hidden units, 40 neurons, or with the black here, which is basically 4,000 units, right? So the black function is much smoother, right? And this function, this previous theorem essentially tells us that we need to find the function h that will still interpolate the data and be as smooth as possible. If you have a straight line, it may be perfectly smooth, but it doesn't fit the data, right? You need to satisfy the interpolation condition and be as smooth as possible. And then the question is, how do I get a function that is as smooth as possible, where this is why I need basically, going back to the previous picture, I need as many parameters as possible, right? Because with as many parameters as possible, I can basically have both the interpolation constraints satisfied and have a function that is, as smooth as possible.
Like having high polynomials as a
right. Right. I mean, the neural networks, right? They can actually, produce. This is why we say that they have a very large expressive power, because they can produce functions, right, that are very smooth if you give them enough parameters. Some other simpler models, let's say a decision tree, may not have enough expressive power to give you, this increased smoothness as we have more and more parameters. Yeah, Spiro?
I'm not sure if this is going to come up later, but where does the training data volume come into this equation?
So this is basically assuming that we have a fixed number of training data, and it's asking the question, how big should the model be for that fixed number of training data? Yeah. Maybe I can give you one more visual kind of explanation of this. So imagine that you are doing binary classification. Of course, this is only in 2 dimensions. You have the blue things and the orange things, right? And you want to classify correctly the blue versus the orange. Essentially, this theorem says that if this is the training data set, right? First of all, you need to have a model that has enough parameters to perfectly separate the orange from the blue. So that may require a model that is, very, very high dimensional to be able to, I don't know what would be a good example here. In order for the model to do this kind of zigzags here, right, to perfectly separate the data, we'll have to have a very large dimensionality, right? And then it's basically the theorem says that if you satisfy that condition, from that point on, basically, you can expect that the test error will only, the error, the test error will only decrease with the number of parameters in the model. So that was, a very surprising and important, I think, discovery in the last few years about not only neural networks, but about machine learning in general. It brought things really, many of the conventional wisdoms were questioned. And now people are thinking very differently about generalization and how to pick the size of your model, right? Okay, this was one thing that I wanted to talk about. Let me move to the second question, which has to do with why does stochastic gradient descent, even though it's such a simple algorithm, a first order optimization, why does it work so well, despite the fact that we're dealing here with non-linearities in the activation functions, right? Remember I told you every unit is a non-linear function. Additionally, typically the loss function that you are using is also non-linear, right? That's another source of non-linearity. And you end up with this kind of very, ugly, maybe loss landscapes that you have to try to minimize your loss function. And typically the initialization is done randomly. So we're not doing any kind of sophisticated initialization here. We just pick weights initially based on some, Gaussian distribution. So again, this was a very big concern about deep learning. But then again, it started from some empirical observations. People were training these models using stochastic gradient descent. I think this one refers to, again, ResNet, trained on ImageNet. And they would find that these are the training error curves. These are the test error curves. They would find that the training error would often go even exactly to 0 or very close to 0. right? So somehow and then, it's not just this plot, right? I mean, there are many papers, empirical papers written where people actually investigated, does the stochastic gradient descent in this case, does this algorithm find just a local minimum, or does it find actually the optimal solution for the parameters, right? And how fast does it? And it would appear again and again that SGD is surprisingly effective, both in terms of the speed at which it finds the optimal parameters and the fact that it actually gives you a zero training loss or close to zero training. So again, this raised a lot of theoretical questions. Several papers were written about the subject. I chose here one of these papers, which tries to explain this phenomenon. And let's look at their main result again. So here, I just need to explain some notation, some terminology first. So N will be the number of training examples, right? D is the dimensionality of the examples. Again, if you think about images, say the number of pixels. Something that is important is how close are the training examples. So you can say that delta is the minimum distance, right, between any two training examples. Why is that important, right? Because think about the very pathological case where you have two different training examples that are essentially next to each other but have a different label. One is a dog, the other is a cat, even though they are so similar. It would be very hard for the model, for any model, to separate them, right? So intuitively speaking, delta is an important parameter that essentially describes how easy your data set is, how close the data set, the data examples are with each other. You would like them to kind of be separated, right? Additionally, we have M, the number of hidden units, of course, related to the number of parameters in the model. L is the number of layers in the network. For now, let's assume that the network is a fully connected architecture. You can extend these results into convolutional networks and other networks. And let's also assume initially that the loss function is L2 regression. Again, this can also be generalized to other loss functions. A little bit of notation. So when you see this notation, fully, it means that this is some kind of polynomial function of x, y, and so on. In computer science, we like this notation of big O, big omega, big theta, right? These are different asymptotic bounds. Theta is an asymptotic tight bound, omega is asymptotic lower bound, omicron is a big asymptotic upper bound. Okay, so what does this theorem say? It's very important that your network is, as we say, overparameterized. What does that mean? That the number essentially of those hidden units, which refers to the number of parameters, has to be essentially larger. Think of it as, let's simplify. Let's just say that this is larger than a polynomial function of the number of training examples, layers, the inverse of that distance, right? So the smaller the distance between the examples, right, it's harder. It gets harder. The problem gets harder. So you will need to have more parameters. So as long as your model is overparameterized in this particular sense, mathematical sense, then what they actually prove is that even if you start from a random initialization of the weights, with a very high probability, close to 1, gradient descent with this particular learning rate. Remember when I showed you the equation for gradient descent, I had this alpha, which was the learning rate. So this is the learning rate. So if you have gradient descent with this learning rate, we'll talk about it in a second, then gradient descent will train your network so that the training loss is less than some epsilon. Okay, you give me the epsilon. I will make sure that the training loss can be less than that epsilon. In how many iterations? In this number of iterations, which of course depends on epsilon. So let's decompose the theorem because there is a lot here, right? A lot of information. So let's decompose it. First of all, the number of training iterations that you will need to get to this, arbitrarily small training loss, it increases, right? With what? It increases with the more examples I have, the more layers I have, right? Of course, I will need more iterations. The closer the examples are, the smaller the delta, I will need more iterations because it gets harder. And of course, the smaller the epsilon is, you want me to get closer and closer to 0. So this will be basically larger, right? I will need more training iterations. So all of this makes sense. Now, what is the relation essentially between epsilon and the number of iterations that we need? Let me ask you this question. Suppose that this is log base 10, and I have an epsilon of, say, 10 to the minus 1. And I decide, I don't know, I don't like 10 to the minus 1. I want me to go to 10 to the minus 2, right? So I decrease epsilon by a factor of 10. How will the running time increase? By what factor it will increase?
2 times.
2 times, right? So in that sense, this is a very good result about how fast the algorithm is because essentially the number of iterations, right, increases in this particular matter with epsilon. You decrease epsilon by a factor of 10, you only increase the number of iterations by 2. What else is interesting in this theorem? I mean, the fundamental contribution of the theorem is that it's telling us that gradient descent, despite its simplicity, despite random initialization, despite all the non-linearities that we have in these networks, can basically essentially give us an arbitrarily small training error, right? In a number of iterations, which increases only slowly, essentially.
This is for the stochastic gradients, right? You see on the stochastic gradients law.
The actual proof, I mean, it's for gradient descent. Again, in practice, we do some engineering tricks, right, to make it faster. But the actual theorem is for gradients. Yeah.
Is there a way to think of this geometrically, the landscape?
To think of it, I mean, there are papers that try to kind of explain things also in that sense. Hopefully I will not oversimplify here, but one of the things that is happening with these loss landscapes is that essentially, even though they can have many, many local minima, right? A lot of these local minima are kind of equally good with the global. So in several cases, it's not about somehow, avoiding the bad local minimum, right? Jumping to another part of the loss landscape where essentially the loss landscape is such that a lot of these local minima are practically. But I remember one of these, I told you there are several papers in this area. One of them, for instance, it makes the point that very often you stay very close actually to that random initialization. You don't jump to a very different part of the loss landscape, which kind of agrees with the notion that essentially no matter where you start from, you will find a good local. I think I have any questions about this part? So again, in practical terms, even though we are often worried about whether we're actually training the model sufficiently well. There is some foundational region. There are some foundational regions, right? That even if you use stochastic gradient descent, it will actually. And maybe I can present it in a different way. If you are using gradients and with all the engineering tricks of stochastic gradient descent with a certain path size and this and that, right? And you see that your training loss is not getting close to zero, right? In that case, I would be worried that maybe something is not kind of well designed in your network. Maybe you don't have enough parameters in your network. Maybe we need to increase the number of layers, the width, this or that. Maybe you don't have enough examples. Maybe you don't. Maybe something else is wrong in terms of initialization or anything else, right? But you should expect essentially your model to, if it is an appropriate model of appropriate size, you should expect it to be able to get down to a training error of almost zero.
So here is that you think only about the training loss.
Right.
So maybe this kind of overfitting eventually. The zero.
That's a great one. Thank you, Martin. I want you to put together now what we learned from the previous part of the presentation, which was all about generalization, all about testing error, and so on, with this part. So you're right, this part has to do with training, right? But what we learned from that previous part is if you go down to a training error of zero, from that point on, you don't need to worry about potential overfitting, right?
You already overfitting regime.
It's not overfitting regime. You already basically, maybe I should example a few slides before. Let's say slide 15.
The test doesn't increase the test loss.
Right. So if you are basically operating in this regime where the training error is close to zero, practically zero, right? You should not basically expect at this point overfitting. You should expect that with a larger network, you will get potentially an even lower. Of course, there are practical trade-offs, right? I mean, so increasing the size of your model, it will take more time to train and so on.
So the base overfitting here is just the first where you can increase.
Yes, the overfitting
is when you are in the overfitting phase, the training error is not zero.
Right, exactly. And the textbooks,
the zero test, zero training error doesn't mean overfit.
No.
Okay.
Typically, what happens is when you are operating in this regime, the test error starts increasing well before the training error is zero.
Is this a general picture or it's just kind of for the ResNet?
I mean, it's not.
It's a generalized behavior. Should we expect always this kind of behavior?
I'm hesitant to answer yes, but in everything I've seen, the answer is yes. So I haven't seen a theorem that proves that it always looks like this particular way, right? But in general, you should, and not only for neural networks, also for other models, machine learning models, right? The general expectation is that there will be a regime where a further decrease of the training error will be accompanied with an increase of the test error, yeah?
In the theorem, they depend on the IID assumption. So, which is fine, but what happens in the non-IID case?
I mean, in the non-IID case, you cannot prove theorems.
Okay.
As far as I know. Yeah, all of these theorems are proved under that assumption. Actually, pretty much everything in theory is based on this.
But applications will be non-IID, right? When people are using it in real applications.
Yeah, I mean, it depends on the application. I'm not sure would agree that if you have a sufficiently large pool of data to choose from, why would I be suspicious that my data will not be independent and I can understand?
Oh, I mean, yeah, it depends on the data. I mean, that's interesting. Like, no,
I mean, I'm thinking about data sets like ImageNet. I have, millions of images, right? Showing different objects and animals and so on. Why would I expect that two images will have some correlation between them? Or maybe like somebody took a picture of the same dog. I don't know, all right, I think we're running out of time. Maybe, yes. I probably have enough time to give you the basic idea for the third one. So about the width and the depth, right? So even in the very old days of neural network research, I'm talking about the late 80s, people proved that even a neural network with a single hidden layer, so it's not a deep network, right? A very shallow network. If it is wide enough, if it has enough neurons, it can represent practically any function, any non-pathological function. So there is, for example, this famous theorem by Sippenko that basically says that if you are working with this nonlinear activation functions are, sigmoidal, so I have, this way, I have these products, right? Weight products of the inputs, the bias term, right? All of these things that we have seen before. Then, with a single hidden layer, that consists of n neurons, n units, I can basically represent any function you give me, any function f that you give me, arbitrarily well, right? If you keep decreasing the epsilon for me, I simply have to increase n. Right? So these are results that actually go back to Kolmogorov, the use of approximation theory. Yeah, like a lot of math from functional analysis and so on. Okay, so this was known for many, many years, but it doesn't apply to deep networks. So more recently, again, in the last 4 or 5 years,
Doesn't apply. That when you consider the hidden layer, both the layers, doesn't apply.
no, I'm saying, it doesn't tell us anything about what is the additional benefit that we get from deeper networks. Also, if we have a deeper network, you may ask the question, can I express any function f you give me with fewer units? So this is what these guys prove, right? Let me tell you about their theorem. They say that if I have a network based on preludes, right? Those linear, rectified linear units, and it's deep, okay. Basically, for any function f that you give me, again, with the exception of some pathological things, right? So when you say the term very integrated function, in my mind, it means practically any function except pathological things. So the function has a dimensionality, from R and R. And for any epsilon that you give me, arbitrarily small, then I can always construct a fully connected relative network that has a width of n plus 4. So n is the number of inputs, right? I can bound, and I can tell you that with a width of n plus 4, I can basically construct a neural network that can approximate any function you give me. You see the difference with the previous theorem, right? Here it's basically more concretely telling you what is the width that you need to represent its function. And actually, if you read the paper, but not the theorem, it actually tells you also how deep the network has to be in order to approximate that function.
This also approximates also when it says the back integral, meaning that the function can be moved except from some countable points where it can be have singularities.
Right.
This is a kind of extension to the previous. The previous was like only for smooth functions, right?
Yeah, but that theorem, from 35 years ago, it has been extended in 1,000 ways.
Okay.
It's a paper that has been cited 20,000 times, actually. And many of those citations are papers that, yeah. Right. Anyway, let me talk a little bit, because we're running out of time, about depth, which is very interesting. Now, the conventional wisdom, if you talk to engineers about how they think about depth, they will tell you that, if I have a deep neural network, the different layers, as I go basically deeper and deeper into the network, I'm learning features that are hierarchical. So in the first layer, maybe I'm learning some very, primitive features like, some lines, some curves, some angles. Maybe if the data set is, faces, human faces, maybe at the second layer, I'm learning basically some representations that are essentially, you can think of them as constructed hierarchically, compositionally from the features that we had in the first layer. So if in the first layer you learn these primitive features here, maybe in the second layer you are learning about the eyes and noses and lips, right? That you can construct by putting together different combinations of these more primitive features. And in the third layer, maybe you are learning faces and so on, right? So this is kind of how people would argue about the depth in more engineering terms. Okay, then this paper came, and there is some heavyweight math here actually for those that are interested. So what these people said is, in the real world, many functions many real-world tasks are compositional, right? What does that mean? When I learn, how to speak, okay, I'm learning, it's a compositional task. I go from the ability to produce primitive sounds and phonemes to the ability to produce words, the ability to produce phrases, to the ability to produce, right? So speech is definitely compositional. Similarly, you can think about vision being compositional, where I learn how to recognize very primitive things and gradually using those, right? So mathematically speaking, let's see how a compositional function would look like. Imagine that I have, the function has 8 inputs in this example, but actually, I'm not thinking about a function where these 8 inputs are combined in an arbitrary way. I'm thinking about functions where the first 2 inputs, x1 and x2, and only then are used by some elementary function h11, right? h11 here is producing some intermediate output. Similarly, h3, h4, they are combined by a function h12 to produce an intermediate output. Then I have this function here, which is h21, right? It takes these 2 intermediate values, it combines them somehow, it produces some other function. Then I have to talk this function h3 at the 3rd layer, right? Which takes all of these intermediate values and combines them, right? So these are compositional functions. And the very important premise of this paper is that in nature, both nature and in technology, many tasks are actually compositional. You can represent them in this way. And under this assumption, if this is true, right? If this is true, then we can prove the following 2 theorems. Let me start maybe from this one. So for such functions, we think of this notation as saying that these are functions with n input variables where you can basically compose them in this way, where you work with smaller functions with 2 different inputs each time, right? So for such, think of them in this visual way. For such functions, if I have a deep neural network, it doesn't have to have exactly the same topology, exactly the same graph with this tree, but it has to include this tree right? So maybe the network includes also other connections, other units, it doesn't matter, but it has to be that the topology of your neural network includes this tree that represents the actual underlying function. So if you have that, then the number of samples basically that you will need in the training process, right? The complexity. So here we're referring to sample complexity, the number of examples that you will need in order to learn this function within an error epsilon is basically bounded by this expression. So again, big O is the asymptotic upper bound notation, N is the number of inputs, epsilon is the error bound, and that is a technicality here that has to do with essentially how smooth these functions are, these elementary functions. So the main result that they prove, however, and I will leave you with that, is that this is such a simple, nice formula, right? It's beautiful. It's basically telling you that if you're comparing this way of learning that function, which is essentially not a deep, not a compositional way of learning it, but you're trying to learn that function with just a single layer. So think of this as your shallow network. And if you think of this as your deep network, how do these two networks compare in terms of the number of examples that they will need in order to learn that function with the same error, the same epsilon? Just a simple formula that says that the number of examples that you will need for the deep network is exponentially lower than the number of examples that you will need for the shallow network. Remember, epsilon is less than 1, right? So if epsilon is 0.1, right? The number of examples that we will need for the deep network is 10 to the minus n, the number of examples that you will need for the shallow network. So that is the fundamental reason we use deep networks. Again, they can learn compositional tasks much faster with many fewer examples, much fewer examples than the corresponding shallow networks, right? So for compositional functions, and if the functional hierarchy is captured by the deep network, the shallow network would need an exponentially larger number of samples than the corresponding deep network to achieve the same generalization error ratio, right? I think I will have to stop here. I kind of unfortunately missed the last part, which was actually our work. Anyway, I'll send the slides to anybody that wants them. All right. Any last questions before we go? Okay. Thank you very much.
Is there any relation between the depth and the width?
Huh?
Is there any relation between the depth and the width?
Yeah, that's actually considered an open question, right? And in some sense, if you would choose like width versus depth, right? If you would choose I give you a budget for the same number of parameters, right? Would it be better to use your budget making your network wider or deeper? And there are some theoretical results about that are essentially, in my opinion, non-conclusive. I mean, a lot of conditions, and it depends on this, depends on that, right? So it's not
the deeper is better.
Yeah, this is
this hierarchical.
Right. This is the gut feeling that most people have, but it's not clear whether it's better because a lot of the functions that we work with in practice are compositional. And if they were not compositional, would it still make sense to use deep networks as opposed to wider and wider shallow networks?
Break down the last.
Yeah. Okay, cool. Thank you very much.